Hi, welcome to another lecture on linear algebra. Today we are going to continue our conversation about Eigen analysis of 3 by 3 matrices. And what's special about the example today is that we are going to have a case of geometric multiplicity larger than 1. Let's see what does that mean. So we want to do Eigen analysis. So we want to find eigenvalues, eigenvectors, and eigenspaces. Find to make it more clear, we are going to ask graph the eigenspace. Okay, as usual, step 1 is to set the determinant of m minus lambda equal to 0 to get our eigenvalues. So that tells us that we want to have determinant of 4 minus lambda, 0, 1, 2, 3 minus lambda, 2, minus 1, 0, and 2 minus lambda. You remember when we talked about determinants, we said we go after the rows or columns where there are lots of zeros to make our job easier. So we expand on this. So it's going to be 0 times determinant of whatever is left, and then 3, or if you wish, minus 0, plus 3 minus lambda times determinant of whatever is left, and this one I better write. I have 4 minus lambda, 1 minus 1, and 2 minus lambda, and finally we have this 0, well, doesn't make a difference, but just to be correct, minus 0 times determinant of whatever is left after that row and column is eliminated. So these two do not play any role because they're going to be 0, and what we have is 3 minus lambda. Determinant of this 2 by 2, this is easy, so we have 4 minus lambda times 2 minus lambda, and then minus 1 times minus 1 equal to 0. We clean this up. Here I have lambda squared minus 6 lambda plus 8 plus 1 equal to 0, and that means I have this peculiar situation. Here's a factorization of that. The root of all 3 parentheses is 0, so lambda 1 is 3, lambda 2 is 3, lambda 3 is also 3. So we can say lambda equal to 3 has also multiplicity. That's going to be geometric, excuse me, we are still doing algebra. It's algebraic multiplicity. All 3 of them are the same. Okay, next we are going to take this and plant it in our m minus lambda and find the null space of that. So next step, I'm going to have m minus 3, so instead of lambda we put its value, and then we ask what's the null space of this. Well, what is that matrix? It's 1 0 1 2 0 2, minus 1 0, and when you put the 3 here you get minus 1. So what does it mean, null space? Null space means we are trying to solve the following equation. Null space means what is it that I multiply by this that I get null, which means I get 0. What are the solutions of this equation? Now it is, we can go to that software we always talked about, but this is, you look at it, second row is double of the first row and the last row is negative of the first row. So let's just indicate we are going to do minus 2 row 1 plus row 2 and row 1 plus row 3. It's rather obvious what's happening. So we have 1 0 1 and this becomes 0, this becomes 0. So it's the first time in the Eigen analysis we are seeing something like this. More than one row is becoming 0, and that indicates what's going to be our geometric multiplicity. If 1 becomes 0, geometric multiplicity is 1. If 2 of them become 0, the geometric multiplicity is 2, and so on. So here, when you multiply, what's the only equation that survives? X plus z is equal to 0. Is that right? The other two equations, just 0 is equal to 0. So how do you solve that? So it's a z, let me take it a parameter. So x is going to be negative of z. So you start to scratch your head. What happened to y? Well, y can be anything. Independent of what these guys are, y can be anything. And that brings in a new parameter. So number of parameters also indicates what is our geometric multiplicity. So if I write x, y, z as a vector, I have what? I have minus t, s and t. We split this thing into two pieces. One t's, the other one s's. And then factor. So t I can factor from this one, minus 1, 0, 1. S I can factor from the other one, 0, 1, 0. Now I have these two vectors. I can say any linear combination of them with any factors is going to be an eigenvector associated with eigenvalue 3. How many linearly independent eigenvectors can I have? I can have 2. So here we indicate 2 linearly independent eigenvectors. Linearly independent means this is not a multiple of that, that's not a multiple of this, truly different vectors. We're not just playing with the t or s. This vector is different from that. 2 linearly independent eigenvectors. That means the geometric multiplicity is 2. You can easily check that these two are indeed eigenvectors. Now, what is the picture going to look like? What's especially the picture of the eigenspace? I go ahead and graph the first one, minus 1, 0, 1. So minus 1 is going in direction of x, and then z. So minus 1, and then 1 is, let's say this is x, this is my y, this is my z. So the first one looks like a vector in this direction. Second one is a vector in the y direction. So a pair of linearly independent eigenvectors. But what's the eigenspace? Any linear combination of these two is an eigenvector of lambda equal to 3. Any linear combination of these two vectors is going to be the plane that is made by these two. So this plane, imagine kind of a door or something with its hinge on the y-axis. It has turned 45 degrees toward negative axis. Of course, this plane extends all over. It's not stopping just here, but we draw a parallelogram on it to indicate what the orientation is. This is going to be the eigenspace. So eigenspace, I can write it like this: all linear combinations of these two for any S and T. Another style of saying the same thing is to say span of these two means exactly the same thing. That's the notation you're going to use in your exercises on WebAssign. So you can say eigenspace is that. You can say eigenspace is the span of these two vectors. So what does it do? It looks like a plane. What's the description of that plane? Well, however you describe this plane here, that would suffice. Okay, so this is an example of a problem where the geometric multiplicity was more than 1. If it is 2, means eigenspace is a plane. If it were 3, the eigenspace would be a three-dimensional space. Let's do a simple example of that as well, as a very extreme example. Suppose I have a matrix and its entries are these. So what is m minus lambda? We want to do Eigen Analysis for this. M minus lambda is going to be 5 minus lambda times another 5 minus lambda times another 5 minus lambda, and all the other entries would be 0. When you set this thing equal to 0, you recover that lambda is, well, it's either 5 or it's 5 or 5. Or you can say lambda is equal to 5 with with algebraic multiplicity 3. Now what does m minus lambda look like? So this was here, determinant of m minus lambda is that. What does m minus lambda look like? When I put the 5 here, I get this peculiar look. Everything has collapsed to 0. Now what's the null space of that? Meaning, what x, y, z can I multiply with this and expect 0? Well, you say anything you put for x, y, z will do it. So what does that mean? It means x is some parameter, y is some parameter, z is some parameter. So x, y, z, just like last time, you can write it as r times 1, 0, 0, s times 0, 1, 0, and t times 0, 0, 1. So eigenspace is going to be the span of these. Eigenspace is going to be the span of these 3 vectors, which are just the basis vectors for R3. So what is the span of these 3 vectors? You have these 3 vectors here. Okay, vector number 1, vector number 2, vector number 3. What's the span of them? Well, the span of that is the entire space. What is the geometric multiplicity? Several ways of counting. How many rows of zeros you got here? 3. How many parameters you got here? 3. How many linearly independent eigenvectors you got? 3. That's all the same. That's the geometric multiplicity is 3. The eigenspace is going to be the entire space, okay, so however you want to indicate this entire space is your eigenspace. Any vector you pick from that and multiply by this particular matrix, all of them are going to become 5 times as bigger as they were. Every vector is an eigenvector, and these 3 are the representatives of all of them. Okay, I hope you enjoyed this lecture and the other lectures we had. Until next meeting, good luck and God bless.